Hey guys, this is Dr. Gonzalez, and this is your lecture video on correlations. So we're going to get involved in some statistics this week that are a little bit deeper than your descriptives and frequencies that you've run, but correlations aren't really that difficult. Um, Remember, a correlation is putting together an association. We are not determining causality. We are simply stating that two variables are related to one another. As one changes, the other one either goes up or it goes down. So that's what you're seeing here. You're seeing a relationship that's going up, a positive correlation. Here we have a negative. And then obviously here I have some spread, and that's nothing. And then over here we just have this graph that's going to show you with our correlation coefficient the different grades that we have to determine the strength of those relationships. So let's get started. The first thing we're going to discuss is how to determine statistical significance and our general approach to hypothesis testing. So we've talked a little bit about null and alternative hypotheses. So let's talk about hypothesis testing. So hypothesis testing is a general procedure in statistics that allows us as researchers to make an inference about a population using sample data, using a hypothesis. Okay. Now, remember, inferential statistics is when I'm making an inference about that population. So I'm not using descriptives. We talked about descriptives last week, and I was very emphatic on some of your homework assignments that descriptive statistics paint a picture. That's it. Yep, it might look obvious that there is a super amount of difference between two variables, and it may seem very obvious that there is an effect going on there, but we cannot make conclusions about anything being more effective or less effective until we have established causation. And before we can establish causation, we have to establish correlation. So how do we do hypothesis testing? Well, this is why we practiced all of the hypotheses writing and things like that. The first thing you've got to be able to do is to be able to verbalize or state a hypothesis about a population. You've got to be able to put that into words, because if you can put it into words, I can put criteria to it that I can use to determine if our statistic is going to meet that criteria or not. So our hypothesis is going to need to predict that characteristic that our sample should have. So if I'm trying to prove that in a population, there's a relationship between X and Y, I need my sample to have those characteristics that are equal to the population so that I can use that sample to make a conclusion about the population, because that sample is representative, right? So I need to have those predictive characteristics there. Next, I'm going to follow my sampling plan. I'm going to make a sample. I'm going to collect data and all that fun stuff. And after I have collected data, I'm going to compare it with my sample and my prediction from the hypothesis. So remember, in statistics, a hypothesis is not like an educated guess. We work from nulls. And a null hypothesis tells me there is no difference between two groups. It doesn't matter the statistic, but whatever statistic I'm running, there is no difference there. So it's very much different from a educated guess that you might have learned about in high school or whatever. So let's talk about stating those hypotheses. So before we get into how we write them, we've got to understand that these two opposing hypotheses that we're going to have, the null and the alternative, they're mutually exclusive. And what that means is they can't exist together at the same time. Either there is an effect or there isn't an effect. There is no in between where there's a little bit of an effect, but there's not an effect at the same time. No, there's an effect or there isn't, and that's it. And we need to state that hypothesis in terms of population parameters. When it comes to hypothesis testing, we've got to have specific decision criteria. We're going to run a statistic, and from that statistic, we need to know what kind of decision we're going to make in reference to the null and the alternative hypothesis. So we're going to set a set of criteria that is related to the probability of getting a certain outcome. Now, we're doing correlation testing here. So when we determine that when we're looking at whether or not that association is consistent with the null, we're talking about high probability values. So if I have a normal distribution here, you can see that there is a small shaded area to the left and a small shaded area to the right. Obviously, I'm going to shade it green here, this green area in the middle here is much larger. So the probability of finding something in that large area is much bigger than the probability of finding something in those two small end pieces. So this green is going to relate to the null. And I'm going to erase this so you can see inside here. It says sample means close to H sub 0. That's the null hypothesis. So if the null is true, then I'm going to get a value that's going to be inside this curve right here, not in the extreme ends. Okay? So if we determine if our association disproves the null, in other words, is our alternative hypothesis true, that means your statistic that you're calculating is somewhere out here in these critical regions that are much smaller. So the probability of finding the statistic hanging out there in the tails is much smaller. So that's how we know when we have done an experiment, and we've run statistics on it. This is how we know that our statistics are correct, because if they fall into those extremes there, well, we caught it, okay? And we're going to talk about error too, so because that can always happen. But this is what you're doing in hypothesis testing. If you are retaining a null, if you are saying the null, remember null means no, so no different. If you're retaining that null, that means that your value fell over here, or over here, or over here, or over here, all right? And if you're rejecting that null, if you are saying that there is a difference, your alternatives are falling out here in these other regions, okay? So as a researcher, you've got to be able to define those decision criteria. And the most frequently used one that you're going to talk about is an alpha level. So we need to set up a specific probability. We're going to call it the alpha level. That alpha level determines those low probability values that are in the tails. And the most common in statistics is alpha equals 0.05. And you have others. You have 0.001, which is very small. And that's really used in a lot of things like your clinical trials, where I need to make sure if there's a difference between two groups, that difference is really there. Well, what am I going to do? I'm going to set my probability to be the smallest amount so that if I do catch a difference, it's extremely likely that it's correct. So what that criteria level does is it sets the most unlikely 5% apart from the likely 95%. So the 5% is in the tails, and we're going to divide it by 2 because there's 2 tails. We're going to talk about what that means in a little bit too. But that 95% where the null is true, where there is no difference or there's no association between two variables, is that main part of your curve. So we are looking at a criteria level. Our alpha levels are going to be where those extreme values are found, so that if we find those extreme values, we are going to reject that null because it's not going to be likely that we find those results if I held on to that null hypothesis. And when you hold on to a null, we say you retain the null hypothesis. All right, So in a correlation, I can do one of three things. One, I can look for a general relationship. Perhaps I'm just exploring some data and I want to find out if variable X is correlated with variable Y. I don't know if it's going to be a positive correlation or a negative correlation. I just want to know if they're related to each other. When we do that, we are doing a two-tailed test. In a two-tailed test, your 5% from that alpha level, it's going to be divided into each tail. So on this side, where I reject the null, I have a 2.5% chance of finding that to be true. And if I'm going to reject the null on this side, I have a 2.5% chance. If I add them together, what do I get? I get 5. Now, most of the time in psychological research, we already have an idea about where those choices are going to go. I said you can say there is a relationship, but I don't know if it's positive or I don't know if it's negative. Well, obviously, my two other choices are these two variables are possibly related. I think they are correlated on a positive level, or I think these two variables are correlated and I believe it's on a negative level. So what do we mean by that? As X increases, Y increases. That is an example of a positive correlation. As X decreases, positive decreases. That is going to be an example of a negative correlation. We're going to go over what those mean in just a moment. I'm sorry, I kind of lost my train of thought there. It's thundering where I am. It's kind of getting a little scary outside. So let's talk about the one-tailed versus the two-tailed. So moving on over to one-tail criteria. When we use one-tail criteria, we are looking at a directional prediction. And let me give you an example of that. So if I have some patients or some clients with anxiety, and I'm working with them on coping skills, I would expect that once I have taught them some new coping skills, so I gave them a new skill, all right, and their anxiety will decrease. Okay, so I teach them a new skill, and what happens? Anxiety goes down. That's a one-tailed test. Because depending on how I'm looking at it, I'm either increasing something or decreasing something. When we do that, it's a one-tailed test, and there is always going to be an association that is either positive or negative with that. So what happens is in a one-tailed test, we take that critical region and we place it all on one side because we want to do our best to maximize the chance of finding a real difference. So if I'm not going to waste 2.5% on my other side of the distribution, I'm going to move it over to the side that I'm looking at. I'm going to make good use of that probability. So this is just, again, showing you the difference between one-tailed and two-tailed. Down here I have my two-tailed because I don't know what direction I'm looking at. I'm simply looking if two variables are related. Honestly, for whatever reason, I don't know if it's a positive or a negative. I have no inkling. So I'm going to do a two-tailed. I'm going to divide that probability in half. Alpha divided by 2. You can see it right there. Very small letters. Alpha divided by 2. And then over here, I have a positive correlation. Alpha is all on the positive side. You can see I have 0 in the middle. And then over here, I have alpha is on my left side. That's negative. And there's just alpha by itself. All right, so one of the problems that we run into when it comes to hypothesis testing are the two types of error that we're going to talk about. The first type of error is called type 1 error. And type 1 error happens when your test says there's an effect, but there really isn't one. In other words, you, the researcher, should have rejected the null hypothesis. but you didn't. So in other words, you said there was an effect when there isn't an effect. And the number one reason that this happens is that your sample is not truly representative of the population. So our hypothesis tests that we're working with, they're designed to minimize the risk of that type 1 error. So that's why we set that alpha level at an extreme end, because the alpha level is a probability that that test is going to give you a type 1 error. So when I hold it at 5%, that means there's going to be some places inside that non-significant region that may show a difference in our variables that we're looking at. They may show a correlation, but you are actually stating that that correlation is not significant because you don't want to accidentally say that something works when it doesn't. We also call that a false positive. Hey, that treatment is associated with better outcomes when it really wasn't. You just said it worked and it doesn't. False positive. So here's an example. So think about it like this. You're testing a new study method. Your new study method, you think it's going to help your students get better grades. You set up the experiment, you do your data collection, you run the statistic, and you come back and say, hey guys, guess what? My study method was associated with higher grades. There was a correlation. It worked. In reality, it didn't work. You just committed a type 1 error. You believed something was true when it actually wasn't. Remember, we call that a false positive. So why do type 1 errors happen? Well, just think about it this way. Anytime you run a statistical test using a sample randomly selected from a population, I caught myself. I was going to say randomly selected, but random selection is it is not needed for correlation, all right? For a true experiment, which is not what this course is about, but for an experiment, you need random sampling. To do a correlation, I don't. So the bottom line here with type 1 error is that anytime you run a statistical test, there is a small chance that for whatever reason, the sample you picked didn't work. You might just have gotten a statistically significant result by random chance. You didn't do anything wrong. Okay, you worked out your magic there. You got your statistic. You said there was a significant difference. There really wasn't. You didn't do anything wrong. False positive. So that's when these happen to random chance. It's still called a false positive. All right, let's talk about type 2 errors. So type 2 errors are the opposite of type 1, obviously. Type 1, type 2, right? So a type 2 error happens when you don't reject the null when you should have rejected it. In other words, your intervention worked, or there was an association between your two variables, but for whatever reason, you didn't find it. Okay, you failed to detect that significant difference. So mathematically speaking, it's impossible to determine the exact probability of making a type 2 error. Remember, making a type 1 error, it's whatever I set my alpha level at. If it's 0.05, that's 5%. If it's 0.001, there you go. Okay, here we don't know what it is, because one of the reasons is that type 2 errors depend on multiple factors. The first one is how variable your scores are. Remember, variability is simply a descriptive statistic that describes how spread out your distribution is, your scores in that distribution are, how much they differ. Another factor that impacts your type 2 error is your sample size. And then the third one is when your effect is weak. So you're trying to detect a difference here. But obviously, if your difference is very small, you run the risk that you might miss it. So, right? But as you can see, there's three different things here that determine type 2 error, and the other one mainly just had one. All right. So think about it like this. You're a scientist testing a new drug to see if it works better than a placebo. And this one is a true experiment. I just wanted to make sure y'all had an example that would really hit home with you. And to me, this is like possibly one of the worst scenarios where this could happen, right? You're a cancer researcher, and the drug that you are researching could possibly save lots of lives. So you're testing to see if it works better than a placebo, and that's an experiment, right? Not an association study like what we're doing. The truth of the situation is your drug really worked. There was a statistically significant difference between your placebo group and your experimental group. But for whatever reason, statistically speaking, you ran the stats, you got that back, you said, no, it doesn't help. So you missed the effect, and you basically concluded that your research drug that you're working with doesn't work, and you could have set lots of people back. Researchers have to go back to the drawing board. Drugs do not pass to the next phase of clinical trials, and people's lives don't get saved when this has happened. So remember, this is a false negative, which would be the opposite of a false positive, right? False positive, hey, there's an effect, and there's really not one. False negative, oh man, there's no effect here, when there really was. So here's a little analogy to help you remember these two things here. I have a smoke alarm right there and some fire. So imagine a smoke detector, smoke alarm, whatever you want to call it. A type 1 error is like when the smoke alarm is going off when there's no fire. So I've had this happen in my home a couple of times, once or twice. It was actually like related to like my son was cooking a pizza in the oven, and maybe like some cheese fell on the little coil things and it burned the cheese and it made some stinky smoke in the house, but there really wasn't a fire. Well, that's type 1 error, okay? Your smoke alarm is going off. There's really no fire. It's a false alarm. The other one, type 2 error, is when the smoke alarm is not going off, but there's actually a fire. So it's not a false alarm, it's a malfunction. And which one of these two things seems to be worse? Well, I don't want to burn up if my smoke detector is not working. Okay? So this is just a little summary table here that tells you just like what's going on and what you should do in certain situations. So I have truth about the null hypothesis in a population. So null means, again, there's no association. So if that's true and I accept the null, I've made the correct decision. Okay? But if I reject the null, I've just committed type 1 error. I said there was a difference when there really was none. And then over here, I also have the opposite of that, truth about the null hypothesis in the population. If I say the null is false, okay, I accept the null, even though it's false, I still keep it and say, hey, there's no difference. I just committed type 2 error. I failed to find a difference when the difference existed. All right, so that brings us to the next portion of our notes, which is what is a correlation? So a correlation is a statistic that measures and describes the relationship between two variables. Okay, so we usually refer to those two variables as x and y, and one of the many ways that you can represent those variables is to use a scatter plot, which is x and y, the x and y axis, perpendicular to one another, one variable on one axis, the other variable on the other, and I get some scores and I plot them, and I use a line of best fit, and then I can tell you if there is a relationship based on, is there something that looks like a line, and does it have a slope to it that I can like see? So in this example that we're going to use in the next few things, we're going to be talking about a kind of silly, like not really related to psychology thing, but I want y'all to see something because I want to talk about how correlation does not equal causality. Okay, just because I say two variables are associated with each other, it does not mean one causes the other. There's a specific set of criteria that have to be met in order for me to determine that a relationship is causal. And a correlation does not meet those criteria, okay? So in this graph right here, we're looking at snow cone sales by temperature. And by temperature, I mean outside, like how hot is it? So what you can see here is as the temperature goes up from 70, 75, 80, 85, 90, what happens to the number of snow cones? Snow cones, raspados, the things that, have the ice and like yummy, yummy, sugary stuff in it. Those things are snow cones. Where I come from, we put lots of the ice and the flavoring, and then you put the condensed milk, the sweetened condensed milk on top, and they're really, really good. But anyway, you might not find a snow cone vendor here in my coastal southern town in the middle of January, okay? But I'm definitely going to find one out there right now in the middle of July, okay? Because there is a positive correlation between temperature and selling and consuming snow cones. When it's hot, you want something refreshing. So a correlation can be used to do several different things. First, we can make predictions because we've got a pattern here. I could say, well, as the temperature increases past 95 degrees, what would I expect this line to probably do? Continue. Okay. No, it might not be true. There might be a different relationship there outside of that. We may saturate ourselves at a certain point with snow cones, but, we can use correlations to do that. We can also demonstrate validity and reliability. And those are two important things that are going to be used in developing surveys. So if you're going to be working with developing your own survey to measure something, you're going to do certain analyses on the items in there. I may have two items that are both meant to assess your current anxiety level at this particular moment, but I'm going to phrase them slightly differently. And I want to make sure those two items are both valid. They're asking a legitimate question about anxiety. So I'm checking validity. And then I would check reliability by saying every time I administer this survey, is it reliably measuring what I want it to measure? Okay. Are there times when I give the survey and it doesn't measure? Maybe it measures something else. So determining reliability and demonstrating validity are two things that we use for survey development of items that use correlation as a statistic to help prove them. And then another one is to verify a theory. So before you can do any experiment where I manipulate my X variable and I expect to see a difference in Y, and I'm saying that there's a causal link between those two things, someone has already done a non-experimental research on that topic and they have correlated something with something else. Okay. Now, with these correlations, as I already highlighted earlier in the day, in this presentation, correlations have a direction, okay? And they're telling you the direction of that relationship. So when that direction of that relationship is positive, that means that you have a change in the same direction. As X goes up, Y goes up too. So as the temperature rises, what happens in snow cone sales? They increase. Okay. Now, a negative correlation is going to be the opposite. So as X variable increases, what happens to your Y? It decreases. So look at our graph here. This is a negative correlation. How do I know? Because my line of best fit is pointing downward. It has a negative slope. Y equals mx plus b. You've got a negative slope there. And this time I'm looking at hot chocolate sales by temperature. So when would you expect to sell more hot chocolate? Well, probably in the winter, right? So right now, you're not going to go run out there and buy your hot chocolates because, not too many people like hot chocolate during the summer. But look, there's always exceptions. You can see them over here in the graph because these are dots and they're all over the place. But if I run the correlation and put that line of best fit in there, I see that overall, I have a negative association between those two variables. So like I said earlier, there are at least 3 kinds of associations. There are actually about 5, I think, but we're not going to go into the U-shaped ones and all that stuff because we're going to keep it simple here. So the shapes that I want you to be associated with for this are the linear relationship. Linear means line, right? And a linear relationship happens, it's indicated when your data points cluster around that straight line. So right here, you have your positive correlation, and you see where all the little X's are? They're clustered around that line. Over here, I have a negative correlation, and again, they're clustered around that line. Now, on the third one, to the extreme right here, you have no correlation. There's no line there because, to me, the best way to describe all of those little X's are they're just like somebody threw them out on a game board, like little dice. They just threw them out. And they just randomly landed. So there's no line I can draw there for best fit. Now, another description of a correlation is a change in X accompanied by a predictable change in Y. And the cool things about correlations is that we can measure that change using a number, okay? So correlations are super easy with interpretation because you're going to get this R coefficient, and a perfect correlation is either going to be +1 or -1. +1 means positive correlation. -1 is a perfect negative correlation. So you can see underneath here, you have an example showing you how that R value, and R value, when we say R value, we're talking about that correlation coefficient, the thing we're going to calculate, right? So it can go from +1 to -1. And I just noticed that this scale is really, it's inherently backwards. Normally we put negatives on the left-hand side and we put positives on the right. So I hope this doesn't throw anybody. But as you move from right to left, you can see that I have a perfect correlation, then I have a high positive, low positive, and none. So depending on your statistical test that you're running and your alpha level, you might find that this is significant and this is significant right here. But depending on what we're doing, that there is a correlation, but it is not significant. You might hear that phrase. There is a correlation. As X changes in general, Y changes as well, but we're not going to consider it to be significant. Obviously, you should note in here that your scores are tightly clustered around that line. I can't draw, obviously, here. I was trying to draw. It's really hard to do with a mouse. So this line right here is indicating that perfect linear correlation. And so the values are tightly packed on that line. But looking at 0, which means no correlation whatsoever, they're all spread out like the randomly thrown out dice that I talked about earlier. So that's your correlation of 0, no consistent relationship between your variables of x and y. So what is the statistic that we are going to use to be able to calculate all of these lovely, lovely correlations? Well, we're going to talk about the Pearson correlation, or the Pearson R. All right, so let's begin our discussion about the Pearson correlation. And I'm just going to warn you, there's going to be a lot of math demonstrated in here. You are not going to be required to do this math. However, I want you to kind of understand the theory behind how they calculate the Pearson correlation. You, however, will be responsible for taking a data set, opening that data set up in Jamovi, and calculating a Pearson correlation and then later a Spearman correlation, okay? So conceptually, correlation, that R value, is the standardized measure of covariance. And covariance is how much two variables vary together, okay? So it tells us that correlation tells us how much two variables change together relative to how much they vary on their own. So it's a ratio. Ratio is when you put two things kind of in a fractional formula. So we're comparing covariance to how much a variable changes or is different on its own. So covariance is going to be positive if those two variables increase together. It's going to be negative if one increases while the other one decreases. And your standard deviations are going to standardize that scale so that a correlation coefficient, the thing that you're calculating in a Pearson's calculation, gives you a score. That R value, it's going to be between -1 and +1. So again, that's why correlations to me are really easy to calculate and interpret, because you've got a value that can only be from -1 to +1. And the closer you get to a -1 or a +1, the closer you are to having a true 100% positive correlation, 100% relatedness, versus 0, where nothing is correlated. So we represent correlation when we're talking about this. We represent it with the lowercase r, and that's going to stand for Pearson's. It's our Pearson's R. Okay. If every change in that x is accompanied by another corresponding change in y, you're going to get that perfect linear relationship. And that's going to look like that. There's our x and our y there, axes there. And if I take this bright red here and I draw a line, and sorry, that's supposed to be red, y'all, but it's coming up pretty dark because of my color scheme here. I have a line that's going straight up. I have, if I put my little dots in there, my dots would be closely clustered around that line, and I'm going to end up having that perfect linear relation. If the change in x does not correspond to that change in y, I don't have a linear relationship. So this is what it looks like if you are to represent this formula we're going to talk about in just a minute on another slide. We're calculating that R, and R is covariance, which is this right here, the degree to which x and y vary together over the degree to which x and y vary separately. So covariability of x and y over variability of x and y separately. So here's where things start to get a little funny looking, right? So some of these formulae you may not be familiar with. the notation that's being used here, that's okay. Really, I just want you to see how that formula on the other page can be broken down into different pieces to actually calculate these statistics. Now, if this was just a statistics class and not a research methods class, I might be expecting you to calculate correlation by hand. I was expected to do it in multiple statistics classes, but that's not the goal of this class. The goal of this class is for you to explore non-experimental measures, and one of the most frequently used statistics in non-experimental measures is a correlation, looking how much two variables vary together. So one of the things that we use in that formula is we are going to have to measure that covariability. And we measure covariability by calculating something called the sum of products of deviations. So this thing right here is called a sigma, and sigma means the sum of something. So if you look, you see I have sum of products. There's my sum right there. I'm telling you, sum of products. What am I multiplying here? I'm multiplying, and that would indicate products. So x minus mean sub x times y minus mean sub y. That's our definitional formula. If you were going to calculate that, you would say your sum of products is equal to the sum of x, y minus the sum of x times the sum of y divided by n, where n stands for the number of observations that you have. Don't feel lost. Just hang with me. You're going to be fine. So here I have a chart, and if you break this down by the formula, you're going to see that I have some scores for x variable and y variable. And then I can calculate, look, I have m sub x is 5 and m sub y is 7.5. So that's my means, right? And my sum of x is 20 and my sum of y is 30. So I can calculate x minus the mean of x. So 2 is my x minus the mean. My mean was 5. 2 minus 5 gives me negative 3. Here I have my x, 4, minus my mean sub x. 4 minus 5 gives me negative 1. And I can continue that all the way down. And I can do the same thing for y. All right, remember my mean sub y is 7.5. So I'm going to take my y score, 3, and subtract 7.5 from it, and I'm going to get negative 4.5. There they are. So remember, negatives are not a good thing. We need to get rid of those, right? So that's where the multiplying, the products comes in. So I'm going to take that negative 3 from here, and I'm going to multiply it times that negative 4.5, and when you multiply two negatives, what happens? They turn positive. So negative 3 times negative 4.5 gives me 13.5. And I'm going to repeat that all the way down for this. And I'm going to repeat it all the way down over here too. This is different. This is my x times y. So just 2 times 3. 2 times 3 is 6. 4 times 6 is 24. So now I can take my, look, sum of products, sum of x minus m sub x, mean sub x, times y minus mean sub y. And I'm going to sum those things together. I'm going to add them up, and I'm going to get 30. And this is just carrying the formula on down here, 30. So then that sum of products gets put into the Pearson correlation calculation. So this table is just brought over, okay? There's your x minus mean sub x and your y minus mean sub y, right? I've got my squared deviations. That was what we did on that other page over there, on that other slide. Then I've got my products of this over here. And remember, I told you the sum is the big deal. So here's where they've calculated my squared deviations for x. I got 20. Over here, I've got my 45 for y. And then remember, we're going to multiply those together, products here. and I get my 30. So I'm going to take that 30 and I'm going to substitute it in this formula here. This formula is the Pearson R formula. Sum of products over the square root of the sum of squares of x times the sum of squares of y. So where do you get the sum of square x? Right there. And your SSY right here. So if I plug that in, I get 30 over the square root of 20 times 45. So bring that over. 20 times 45 gives you 900. The square root of 900 is 30. And bring this 30 over. What is 30 divided by 30? 1. So this right here is a perfect positive correlation. So when you go back to your hypothesis testing, when we're talking about correlations, we're talking about whether or not something is correlated or associated with another variable. So remember that your H is for hypothesis. H sub 0 is my null hypothesis. And this funny looking thing right there is a rho, and rho stands for that R. So it's the Pearson coefficient. So if I was going to write a hypothesis test set of hypotheses, a null and an alternative using math for a correlation, I'm going to write that right there and say that there is no correlation because I said that my R, my rho, is equal to 0. And we know that when that correlation coefficient is calculated and it equals 0, there's no correlation. Now, anytime it is anything other than 0, it means there is a correlation. Our hypothesis testing is going to help us determine whether or not that correlation is statistically significant or not. I can also make a prediction about the direction of that correlation. I can tell you that rho is less than or equal to 0. It's not a positive. Or if it's greater than 0, it means I have a positive correlation. So in other words, if it's anything other than 0 going to the right and not a negative number there, it's positive, and the opposite would be true if you had a negative. So if we were calculating our Pearson correlation by hand and not using Jamovi, we would need to use something called the Pearson correlation table, which I'm going to put this in Canvas, but it's also located in that Gravatar textbook in the back. It's a table, and you're not going to need to use this when you're working with Jamovi. Jamovi is going to give you your critical values a little bit differently. But anyway, if you were doing it by hand, you would need to determine your critical values. So I need to calculate my degrees of freedom, which my degrees of freedom is simply the number of observations minus 2. So if I have an N of 4, 4 minus 2 gives me 2. I'll write down here, 2. And every test is going to have an alpha level. So our alpha level in this class is going to be 0.05 all the time. And then depending on what kind of correlation you're doing, if it's one-tailed or two-tailed, you're going to look in a different place in this particular table. The example I'm giving you here is I want to know what the critical value is when N is equal to 4 and I set my alpha level at 0.05 in a two-tailed test. So I'm looking for a statistical significance either on the left negative side or on the right positive side. Okay. And I've set my alpha level at 0.05 and my N is 4, so my degrees of freedom is 2. So I'm going to go in this table up here and I'm going to trace over from degrees of freedom, N minus 2, and there's a 2 behind there, right? And then over here I'm looking for my two-tailed test at 0.05 and bam, that is my critical value. So if I calculate an R, that is 1, a perfect correlation, 1 is greater than 0.95. So I would reject my null because there is a statistically significant difference between those two numbers. That means there is an association, it was positive, and it was statistically significant. Now, as with everything in life, there is a limit with hypothesis testing. One thing that people tend to do is that they focus on the data rather than the hypothesis. And by that, they say things like, oh, look at this data here. When I run this scatter plot, it looks like I have a linear relationship and it's positive. That's great, but until you've ran that Pearson correlation and get that actual statistic and compare that statistic to the critical value, you cannot say that that relationship is statistically significant. You could say there's a relationship, but you don't know if it's statistically significant or not. So another problem is that you might have a significant association, but depending on what your levels are, that correlation, that association might not be substantial. And that means you can have a tiny little correlation that is statistically significant, but in reality, those two variables are not strongly related. So here's an example. So if you collect data on 10,000 students, and that's a really big N, researchers really don't get a chance to do research with a sample that big, okay? And that's the problem here. If I collect data on 10,000 people, and I look at their height and their GPA, with R equal to 0.05, that is statistically significant, but it is not substantial, okay? There is a correlation between height and GPA. The problem is being taller doesn't affect your GPA. So what was the purpose of finding that correlation? Well, there was no purpose behind it. It doesn't tell you anything useful. So you just have to be careful. We have to look at effect size. And you've got to temper that with your results to be able to talk about whether or not a real association that is significant and substantial exists. So effect size itself is a measure of the magnitude. How strong is that association, that relationship between those two variables? How strong is it? And this is useful because it tells you and your readers when they're reading your published work, right, about your correlation, it tells how important your results were, and it also indicates the accuracy of your association, okay? So in this table here, we have Cohen, a statistician. He has this thing called the Cohen's rules of thumb for effect size. So I have my correlation coefficients. These are the things that I'm calculating. These are my R values, okay? I have R equals 0.1. Remember, R can go from -1 all the way to 0, all the way to +1, okay? And right here I have 0.1. So that's right, we're going to put it right there, okay? And what that means is the difference between your means in that calculation is 0.2 standard deviations. That's not a lot of standard deviation, not even one standard deviation, right? So it's on the low end there. Well, this would correlate to a small effect size. So maybe that's important. Maybe depending on what we're studying, that's significant and substantial. And it might not be, depending on what you're looking at too. A medium effect size. So let's look at our 0.3. So I'm going further up here. If I divide that 0 to 1 there into 10 little dashes, 3 is going to be right there. So what happened? I just knocked out a small amount of my critical region there. I'm making it harder to find, but at the same time, that medium effect, it's a stronger effect. So those two variables would be more highly correlated with one another. And then bam, I get down here, R equals 0.5. That's about halfway between 0 and 1. No, it is halfway between 0 and 1. I get a large effect size. And my standard deviation to that, you can see it's getting bigger. D is equal to 0.8 standard deviations. And that's your difference between means. So this leads us into how do we as a researcher interpret our correlation coefficient? So the first thing you've got to remember is that correlation does not equal causation. So when my professor was teaching me this in college, in undergraduate statistics for the first time, he liked to talk about, when we got to correlation, he would talk about how eating ice cream is correlated to drowning. Okay, so I want you to think back to the little research scenario at the beginning, the graphs that I showed in the beginning that said as temperature increases, the number of snow cones consumed increases, right? And we had determined that the reasoning behind that would be it's hot. So it makes sense, right? The hotter it is outside, the more likely people are to go buy ice cream, right? So the same thing's true with swimming. So the hotter it is outside, the more likely people are going to go swimming. And what is true about drowning? You're more likely to drown if you're in the water, and you're more likely to be in the water if you are doing what? Swimming. So I can say there's a correlation between eating ice cream and drowning. But that really means that eating ice cream, swimming, drowning, and high hot temperatures outside are all correlated with each other. How can I determine what is the effect of one variable on the other? That is causation. When you're getting into causation, you're looking at why something is happening, not is it happening. Correlation is telling you this is happening. It's a relationship. But correlation is not causation. So why? It does not establish what we call temporal precedence. Precedence means it takes place first, and temporal has to do with time. So when we say a correlation is not causation because it doesn't establish temporal precedence, it means that we don't have a X causes Y relationship because X happened before Y in time. First, you got therapy, then I tested to see how depressed you were. That's temporal precedence. What if I tested you for depression before therapy? Well, that's a baseline. That's great. We need that sometimes. But I can't take that and 100% attribute therapy to reducing those depression symptoms if I haven't done an experiment that was set up the right way. So we've got to have temporal precedence for a causative relationship. And then you've got to worry about confounding variables, right? Third variables that influence both. So think back to ice cream, swimming, drowning, and summertime. What is one thing that is consistent between all of those variables that we can say confounds the whole situation? Temperature. The hotter it is, the more people go swimming. The hotter it is, the more people might eat ice cream. Then you can go into the other part. The hotter it is, people are likely to swim. What happens? They're likely to drown if they are swimming. You know, people don't drown when they are not swimming. I mean, you can, but in general, right? You can assume someone during the summer who drowns was swimming. But I can't attribute that relationship to swimming if I don't control for other things, okay? Like ice cream. I could later make the statement that there is a high correlation to eating ice cream and dying during summer. Why? Well, if dying from drowning specifically, if I correlate one with the other, I don't know how much that influence is from each variable. So a correlation alone does not describe how accurately that variable is going to predict another. So you're going to get this thing called the coefficient of determination, which is r squared, and it measures the proportion of variability in one variable that can be determined from the relation with the other. So if r squared is equal to 0.5 squared, 25%, if you know x, you can partially predict y. Why? Because 25% of that variability between those two things is related to the other variable. All right, so we've talked about the Pearson correlation. Let's talk about the alternative. We're going to cover one major alternative in here, maybe two, but you're only going to be responsible for calculating and interpreting, and by calculating, I mean with Jamovi, Pearson and Spearman correlation. So let's talk about some alternatives, including Spearman, to the Pearson's R. So the Spearman correlation is going to measure the relation between x and y when both variables are measured using an ordinal scale. Okay. Now it can be used when there is not a linear relation between interval or ratio data as well. So remember, ordinal is not the same as that continuous variable that we were talking about in those other situations with measurements, right? So there's going to be some times when you might need to convert a raw score into ranks so that you can do the proper analysis. And then sometimes when you're converting those things, you might come out with a bunch of scores that are tied or the same, and so you might have to use an average rank. Okay, but you're not going to have to worry about that particular concept in your calculations. That's the formula for your Spearman correlation. And yes, it is a little bit different from your others. You've got a d squared in here where that d is the difference between x rank and y rank. So this is just showing you how they would calculate it. That is obviously a lot of numbers and a lot of craziness. So you've got your original data, 6, 8, 20, 22, 24, and then over here you've got the y. You can list your x in your ranks, 1, 2, 3, 4, 5, and then your x squared. Okay. 5 times 5 is 25. That's where you're getting that. Same thing with y. 5, 4, 3, 2, 1. They just ranked them. And you can calculate all that out until eventually you can get the sum of d squared, which is 38. And if you go down here and you look in your formula, bam, right here. There's your d squared. There's your 38 that came from there. Okay. This is just, again, it's a mathematical summary. I don't want you to have to worry about what in the heck is all of this stuff. In the end, though, you get something that looks a lot like a correlation coefficient. I've got R sub S, which is S for Spearman, is equal to negative 0.9. So that looks surprisingly a lot like a Pearson's correlation coefficient there, okay? So what I want you to understand is how to do hypothesis testing with that Spearman correlation. Remember, your objective in a hypothesis test is to determine whether your correlation exists in the actual population using a sample. So here I have my null hypothesis. It says the population correlation is 0. And then underneath it, my alternative is that there's a real correlation in the population. And you may notice that I'm using correlation here And if you didn't know I was talking about that ordinal data, you wouldn't know if I was talking about a Pearson versus a Spearman. Okay? So you got to be careful, and you got to read the context of the problem or the situation or whatever to know if you're dealing with Spearman or with a Pearson. So just like with your Pearson, you're going to have a table that's going to help you identify your critical value. And remember that critical value is if you were doing this by hand, all right? So what you would do is you would determine where you're going to draw your line for what is significant in a Spearman correlation using a Spearman correlation table, which is different from a Pearson. It looks similar, it's the same concept, because remember Spearman is also going to be -1 to +1, but instead of using n, we use n instead of the degrees of freedom. Remember, degrees of freedom was my total number of observations minus 1, right? Or no, minus 2, actually. And n is just my number of observations. So if my n is equal to 5 and I set my alpha level at 0.05 and I go over this table, I would find there's my 5 for my n, and there is my significance level for a two-tailed test at my alpha equals 0.05, and I would see that my significance is 1. So my critical R sub S equals 1 for a two-tailed test. Now, look at what happens as you increase your n. If I only had 5 participants, I would have to have a perfect correlation for me to be able to detect it under the rules of this particular significance testing for that hypothesis, right? But if I double the number of people in my sample and I keep my alpha level in two tails at 0.05, I can detect a difference of 0.648. I have much higher probability of finding that difference with 10 people than finding it with 5. So another alternative to a Pearson's correlation is what's called a point biserial correlation. And we use those when we are measuring the relationship between x and y when I have a dichotomous variable for one of my variables. Either x or y is dichotomous. And dichotomous means there's only two options, and those options are 0 and 1. So it's calculated using the same formula for Pearson's, except we are going to calculate what's called a phi coefficient, that funny looking Greek letter right there. And it's calculated when both variables, the phi is calculated when both of my variables are dichotomous. So what we would do is assign the values of 0 and 1, and we would use the Pearson correlation formula. So that might be a question on the test, but you are not going to have to do any point biserial correlations in Jamovi. So that's a great segue here to the important part of my teaching is how do you do this in Jamovi? What does it look like, and how are you going to be able to do this when it comes to your assignments and your tests?